Welcome, everybody. I'm very happy to introduce Patrizio Frosini. Patrizio graduated in Florence, where he also got his PhD. For his PhD thesis, he invented what was called at the time size functions, later to be included into what is now called persistent homology, something which is really widespread in research, theoretical and applied. And at that time, it was already very important, the stress given to the observer, in the sense that there was the use of different filtering functions, and that was already a particular attention to the role of the observer in comparison with data. And in the last few years, that became something formal, because Patrizio then also started working at what you can see in the title, a group equivariant non-expansive operators, where the observer is actually formalized. Patrizio worked for a very long time in Bologna, my alma mater, and in the last few years we lost him to the great University of Pisa, Department of Computer Science. Okay, so I'm happy to give the way to Patrizio to start his talk. And I think I'll have a look at the chat if anybody wants to. If you want to write something on the chat, then I'm able to interrupt Patrizio if necessary and read what you write. Okay, Patrizio.
Thank you so much, Massimo, for the introduction, and thank you to the audience. It's a pleasure to be here to speak about group equivariant non-expansive operators. So, good morning and good afternoon, and I start. This is a plan of my talk. I will start from some epistemological assumptions, then I will explain what a GENEO is and some properties, some mathematical properties, the way of building GENEOs, and some connections with topological data analysis and explainable artificial intelligence. Okay, let's start from the epistemological assumption. The first assumption concerning the building and the theory of GENEOs is that data are processed by observers. There is no meaning in data without an observer to interpret them. Observers, what are observers? Observers are agents that transform data while preserving their symmetries. Another important assumption is that observers are variables. We cannot have an absolute observer. We have to change observers, and data interpretation strongly depends on the chosen observer. When we change the observer, the judgment about data can completely change. The third assumption is that observers are quite important. We are rarely directly interested in the data, but rather in how observers react to their presence. If I have a skin lesion, the image of a skin lesion on my skin, I'm not interested in the image. I'm interested in the reaction of my dermatologist to the view of this skin lesion. And this is a general principle when we speak about data. Consequently, the most interesting thing is not studying the shape of data, but rather studying the shape of observers. And finally, another important assumption, there is no structure in the data. When we speak about structure in the data, we are speaking of something projected by the observer. It is a property of observer that is projected to another space. The shape is not in the data, but in the eyes of the observer. So on the basis of these assumptions, let me start defining the theory of the concept of GENEO and the theory of GENEOs. The question is, how can we translate these ideas into mathematics? We have data and we have observers. How can we formalize these concepts? In this approach, the approach I'm going to describe, data are described by perception spaces and observers by group equivariant non-expansive operators, GENEOs. What is a GENEO? A group equivariant non-expansive operator is a mathematical tool used to approximate observers that act on data. The theory of GENEOs is based on the idea that the geometric characteristics of observers significantly influence the interpretation of data. And in this talk, we will explore the core properties of GENEOs, examine their role in machine learning, and discuss their promising applications in explainable artificial intelligence. Okay, so this is the general plan of my talk, illustrating these operators. Some basics on the theory of GENEOs. We have to start with the definition of a perception space. I recall that a pseudometric is just a metric without the property assuring that when the distance vanishes, then the points coincide. Here we haven't this property, okay? So we can have two objects with a vanishing distance, but they are different from each other. So in order to define the perceptual space, let us consider a non-empty set, capital phi, endowed with a pseudometric d phi. And the group G acting on phi on the left. And what we require is that this action is by isometries. So we need that this equality, can you see my pointer when I move around on the screen? Can you see my pointer?
Yes.
Okay. So we need this equality here. Our action must be by isometries. When we have a group acting on a set phi, capital phi, by isometries, we say that we have a perception space phi G. What is phi? Phi is the set of the data that are legitimate in our analysis, that we can accept in our analysis. Think about functions, graphs, point clouds, okay? Different kind of data. And the group G represents the possible transformations of the data that the observer may be interested in. Just a few examples. We can consider phi as the set of gray level images viewed as functions from the real plane to the closed interval 0, 1, when we endow this space with a subnorm distance. And then the group could be the group of isometries of the real plane. We move around the images, okay? Or we could consider phi equal to the set of all subgraphs of a given graph gamma endowed with a distance for which two graphs have distance 0 if they are isomorphic and one otherwise. And G is the group of graph isomorphism of graph gamma. Or we could choose to work with the set of non-empty compact subsets of real plane endowed with the Hausdorff distance. And in this case, we could choose to take G equal to the group of isometries of the real plane. So many possible cases can be considered. Please observe that when we have a perception space phi G, we can define a pseudometric on the group G2. This pseudometric dg is defined like this. The distance between two transformations in the group is just the supremum varying phi in the set of legitimate signals, legitimate data, of a distance d phi between G1 star phi and G2 star phi, where star denotes the action of the group. Okay? It is interesting to notice that the two following statements hold. G is a topological group with respect to our metric and the topology associated with that, and the action of G on phi is continuous. So we can start with mathematics at this level. And now I can introduce the concept of GEO, group equivariant operator, and the concept of a GENEO, group equivariant non-expansive operator. These are the concepts that we use indeed in artificial intelligence to represent observers. Let phi g and psi k be two perception spaces. So phi are some kind of data where the group G act on, and similarly for other data psi and another group K. If a map F from phi to psi and the group homomorphism T from the group G to the group K are given, such that we have this equality here that we call equivariance, we say that Ft is a group equivariant operator. If F is non-expansive too, that is, this inequality holds, then we say that Ft is a group equivariant non-expansive operator, a GENEO. You can observe that there is something asymmetrical here. I'm requiring here an inequality concerning the distance about data, but not a corresponding inequality concerning the homomorphism T. We do not require that the homomorphism is non-expansive. Why? The reason is that when we have a geo Ft, and we assume that F is surjective, and this is the general case, I can explain the reason for that, but generally speaking, F is surjective. In this case, the non-expansiveness of the map F implies the non-expansiveness of the homomorphism T. So it is useless under this assumption to assume that T is non-expansive. Let me give you some example in order to see that GENEOs are pervasive in applications. Image blurring. Let us consider the collection of all color images viewed as compactly supported functions from the real plane to the space of colors, endowed with max norm distance. Okay, so E is the space of color images, and F is just a convolution taking I to I that is associated with the kernel K, where K is rotationally symmetric and has an L1 norm equal to 1. Okay? If we consider this map, this convolution, and the homomorphism given by the identity between the group of isometries of a real plane to itself, then we have a GENEO. Ft is a GENEO. So we can say that image blurring is a GENEO. What does it mean? It means that when we consider an image, as you can see here, a color image, if you blur the image like this, and then you rotate the image, or you apply another movement, a rigid motion to the image, you obtain the same result that you can obtain by first rotating the image and then applying the blurring. So we have equivariance. And also we observe that blurring does not increase the distance between the image, where the distance is the max norm distance. So we have non-expansiveness, equivariance and non-expansiveness. Image blurring is a GENEO. Another example is the computation of convex hulls. Let us consider the collection S of all finite non-empty subsets of a real plane, and P the collection of all polyhedra in the real plane. And now let us consider the map F taking each set in S, each cloud of points, let me say, to the polyhedron that is given by the convex hull of this cloud of points. And then we take T, the homomorphism between the groups that in this case are just the group of rigid motions of a real plane. We take T equal to the identity. Then, once again, Ft is a GENEO. And the reason is trivial. If you compute first the convex hull and you get a polyhedron, and then you move a polyhedron, you get the same result that you get when you first move the cloud of points and then you compute the convex hull. And also, if you consider as a distance between compact subsets of a real plane the Hausdorff distance, you have that the operation of taking the convex hull does not increase the Hausdorff distance between sets. So our operator is non-expansive, equivariant and non-expansive. Computing convex hull is another example of GENEO. Maybe it is more interesting to consider the third example. Computing persistence diagram is another example of GENEO. Let us consider DGM, that is the collection of all persistence diagrams of real-valued continuous functions defined on a topological space X, where DGM is endowed with the bottleneck distance, the usual bottleneck distance. Then we consider the map F that associate to each function here, to its persistence diagram. Okay, in degree K. We choose a degree K and then we compute the persistence diagram. If we do that, and we take as T the homomorphism that takes the group of any possible homomorphism of a topological space X to the identity between persistence diagrams, then we have that Ft is a GENEO. So when we compute persistence diagrams, we are computing a particular example of GENEO. Let me rephrase this in a different way. The equivariance of this operator is the invariance of persistence diagrams under reparameterization of the domain. And non-expansiveness of Ft is equivalent to the stability of persistence diagrams. So two important properties of persistence diagrams are contained in the concept of GENEO. And this is this was the first reason to start studying GENEOs. Why are GENEOs interesting? GENEOs rest on a rigorous topological geometric framework, and in what follows we will outline several results. They encode prior knowledge about the chosen observer. The non-expansiveness property of GENEOs imposes a strong constraint that enables meaningful data simplification. GENEOs enable a compositional approach to deep learning. And finally, analyzing the geometry of observer space as represented by GENEOs is often more informative than analyzing the geometry of data space. Shape is in the observer, not in the data. So, what is the main point in this approach from the applicative point of view? In perspective, we are looking for a good compositional theory for building efficient and transparent networks of GENEOs. Some preliminary experiments suggest that replacing neurons with GENEOs could make some applications in deep learning more transparent and interpretable and speed up the learning process. This is a general idea. Before proceeding, giving you some theorems and explaining some concepts, I'd like to say something about some research projects concerning GENEOs. There is a project on GENEOs for 6G. 6G, as you probably know, is the new standard for mobile communication. And this is a joint project with Huawei, and where we are applying GENEOs in order to reconstruct radio signals. Another project is this project Pandora. It is an Horizon Europe project where there is a task that concerns the application of GENEOs for reconstructing, for changing data in a way that are of use for explainable AI. And another project is GENEONet. What is GENEONet? It is a web service representing the outcome of a partnership with the Italian pharmaceutical company Dompe Farmaceutici. And it is a web service to locate pockets in proteins. You can play with this web service if you wish. There is the link here. As for the link, I will make, if you are interested in these slides, this presentation, you can download these slides from the link I will make available on the chat at the end of my talk. And if you use this web service, you can insert a protein and ask GENEOs to look for pockets that are the locations where some molecules can join the protein in order to change the activity of this protein. Okay, these are just examples of the use of GENEOs in real applications. Let's go back to mathematics. Compactness of a space of GENEOs. From now on, I will use this symbol, F all T, to denote the set of all GENEOs Ft from a perception space, capital Phi G, to another perception space, psi K, where we fix the homomorphism T. T is fixed here. Okay? We equip F all T with the following distance. We use this distance for comparing GENEOs. Please pay attention that capital Phi is not a vector space in the general case. Okay? We use here the psi as a metric on capital psi. Now we have this theorem. If the perception spaces are compact, then the space of all GENEOs is compact too. And this is interesting and useful. Interesting from the mathematical point of view and useful for applications. Let me say something more about this. The compactness of a space of GENEOs is an important property from an applied standpoint. It implies that a space of GENEOs can be approximated arbitrarily well by a finite set of GENEOs, and that every continuous loss function defined on this space attains an absolute minimum. Okay? So this is important. Convexity. Now let us assume that phi and psi, the space of data, are normed real vector spaces. And in this case, we consider the distances induced by the norms. Okay? And let us also assume that the group actions are linear. So this equality holds. Okay? Under this assumption, in this particular case, we have that if F1T, F2T, Fnt are GENEOs from phi g to psi k, and we take an antipole in Rn such that this inequality holds, then we can define this operator, F sigma, that is just the convex combination of Fi by using our coefficients AI. And in this case, we have that F sigma T is a GENEO. As a consequence, the space F all T is convex. So, under suitable assumptions, we have compactness and convexity of a space of all GENEOs. Two key observations. While the space of data is often non-convex, and hence averaging data does not make sense, the assumption of convexity of psi implies the convexity of the space of observers and allows us to consider the average of observers. And this is quite useful in applications. Our main goal is to develop a good geometric and compositional theory to approximate an ideal observer. In our model, to approximate an observer means to look for a GENEO f that minimizes a suitable cost function C of f. The cost function quantifies the error that is committed by taking the GENEO f instead of the ideal observer. Since the space of GENEOs is compact and convex, under the assumption that the data spaces are compact and convex, if the cost function C of f is strictly convex, we have that there is one and only one GENEO that best approximates the ideal observer. Now, let's limit ourselves to consider a particular case of GENEO, the functional case. This is a particularly important case in applications. It is the case where the perception spaces involved in the process consist of sets of data expressed as functions, okay, with values in R or Rn. And in the remainder of this talk, I will restrict the attention to the case of data expressed as real-valued functions. In every perception space phi g under consideration, from now on, capital Phi will be a set of R-valued functions defined on a domain X, denoted by dom of phi, and endowed with a metric induced by the max norm, value infinity distance. The group G will be a group of permutations of X such that if phi is a legitimate signal and G is a legitimate transformation, then this composition, phi composed with the inverse of G, still belongs to the set capital Phi. And the left action of G on capital Phi is given by this equality. Okay? We observe, and this is important, that this action is isometric. So we respect the definition of perception space. Building GENEOs. After defining GENEOs, we have to build GENEOs in order to use them in applications. In order to use our model profitably, we need constructive methods to produce GENEOs in the presence of pre-established data and equivariance groups. I will not give technical details here, but it is easy to state these propositions. The composition of GENEOs under reasonable assumptions. The composition of GENEOs is still a GENEO. The maximum and the minimum of GENEOs are still GENEOs. The translation of a GENEO is still a GENEO, and the convex combination of GENEOs is still a GENEO, as we have seen previously. This is trivial in some sense, but quite useful in application. We can use GENEOs as bricks to build more complex GENEOs. But there is much more than that. I would like to say something about a particular way of building GENEOs, the way that is based on generalized permutant measures. Let us consider the set capital Phi, that is the set of functions from a finite set X to the real numbers, that is isomorphic to Rn, the set of all functions from X to R, and the subgroup G of a group of all permutations of X, out of X. Similarly, let us consider the set of all psi of all functions from Y to R, where Y is a finite set, and we take a subgroup K of a group of all permutations of Y, out of Y. And then we fix a homomorphism T from G to K. This homomorphism, meaning, probably I should say something about this, it is the way of understanding which transformation in G, so in the first perception space, corresponds to which transformation in the other word, let me say, where we have to work on data. Now, a finite signed measure nu on the power set of all functions from Y to X is called a generalized permutant measure if each subset H of a set of functions from Y to X is measurable, and the measure of a singleton containing just the function H is equal to this measure, okay, for every G and every functions in XY. This concept was introduced in this paper, Generalized Permutants and Graph GENEOs. Now, let me give you an example of permutant measure, a simple example, maybe a trivial example. Let us consider the set X of the vertices of a cube in R3 and the group G of orientation-preserving isometries of R3 that take the vertices of a cube to the same set. Here, we choose Y equal to X and K equal to G, and T, the homomorphism, is naturally chosen equal to the identity, since the group are equal to each other. Let pi 1, pi 2, pi 3 be the three planes that you can see in the picture. More precisely, they are the planes that contain the center of mass of X and are parallel to a face of a cube. Now we consider the maps that are the HI, that are the orthogonal symmetries with respect to the planes, pi i's. We can now define the permutant measure mu, the power set, the set of any possible subset of xy, by setting mu of h1 equal to mu of h2 equal to mu of h3 equal to a positive real number, and the measure of the other singleton vanishes. Okay, this is an example of permutant measure. So we can build permutant measure. What is the reason of introducing permutant measures? The reason is the following representation theorem for linear GENEOs. If the image of a group G, that is a subgroup of group K, acts transitively on the finite set Y, and F is a map from Rx to Ry, then the pair Ft is a linear GENEO from Rxg to Ryk if and only if there exists a generalized permutant measure mu such that this equality holds for every phi, for every admissible data phi, and the total mass of a measure is less than 1. So what we have is that for any linear GENEO, we have a permutant measure, and for any permutant measure, we have a linear GENEO. So we have a recipe to build any possible linear GENEO under the assumption of our theorem. If you wish to have more details about this theorem, there are these two papers on the finite representation of linear group equivariant operators via permutant measures, and this recent preprint, an algebraic representation theorem for linear GENEOs in geometric machine learning. Now, I have to say something about GENEOs and topological data analysis, since I'd like that the link between GENEOs and topological data analysis is quite clear. Okay, we have already highlighted that the computation of persistence diagrams can be formalized as a GENEO. Computing a persistence diagram means computing a GENEO. And in my opinion, this is a sufficient reason to be interested in GENEOs, at least for people working in topological data analysis. However, there are also other interesting connections between the concept of GENEO and topological data analysis. And in what follows, we will illustrate some of them. Okay, the use of GENEOs, first of all, the use of GENEOs allows us to restrict the invariance of topological data analysis to subgroups of a group of all possible homeomorphisms of a domain X that preserve the space of data phi. I mean that when we compose one of these homeomorphisms with a function in capital phi, we get another function in capital phi. Okay? And this property that is related, mainly related to persistence diagrams, is not so good. Since if you are interested in data analysis, we wish to distinguish between a letter P and a letter O, for example. If we consider these objects in the real plane represented by a subset of real plane, I mean not just line, but thick sets, okay? We have that these two subsets of real plane are homeomorphic. So when we apply directly topological data analysis to these data, we obtain the same persistence diagram, okay? And this is not good in application. So what we wish to do now is restricting the invariance of topological data analysis, having some kind, let me say, of persistence diagrams that are not too invariant, okay? So in order to do this, let us assume that a set F of GENEOs from a perception space phi G to a perception space psi K is given with respect to a fixed homomorphism T from G to K. Let X denote the domain of the functions in capital phi. Then for every degree K, we can define a new pseudometric on capital phi by using this equality, this formula. What does it mean? It means that instead of comparing by the matching distance the persistence diagrams, DGM is the persistence diagram, the persistence diagrams of phi 1 and phi 2, we compare the persistence diagram of f of phi 1 and f of phi 2 when f varies in the set f of our GENEOs, okay? And we take the supremum. So in this way, we obtain a new distance that is not the matching distance, but another distance based on this set of GENEOs we have chosen. It is interesting to observe that the distance between, if we take a function in capital phi, so one of the data we are interested in, and the transformation in our group, capital G, when we compose phi with G and we compute our distance between phi composed G and phi, we get 0. And this is what we want. We have invariance with respect to of data with respect to the action of our group. But in general, due to our definition, this is not true for any homeomorphism in this group. And this is exactly what we wish to have. Okay? So we can restrict the invariance of TDA using GENEOs. It is also interesting to observe that since GENEOs are non-expansive, the new pseudometric is stable. So it is less than the maximum distance between the data. Okay? And this is a good reason, in my opinion, to consider GENEOs. Let me add that we can compute this thing, since we can observe that if phi is compact, and in many applications data are a compact space, the pseudometric we have defined can be approximated arbitrarily well by a finite subset of operators. We haven't to take any possible GENEO, an infinite set of GENEO. We can work on a finite set of GENEOs. Indeed, this proposition holds. Assume that capital phi is compact. Let F be a non-empty set of GENEOs from the perception space phi G to the perception space psi K, where the homomorphism T from G to K is fixed. Then for every positive value epsilon that represents our error, there exists a finite subset F star of F such that this inequality holds. So we have a good approximation of a matching distance, not matching distance, this distance associated with F, with the distance associated with a finite set F star. Okay? It is important to stress that this statement follows from the compactness theorem for the space of GENEOs that I have illustrated before. Okay. Another reason to be interested in GENEOs is the following one. Let us consider biparameter persistent homology. I do not know if this concept is familiar to you. Anyway, assume that bold phi, that is a function with two components, it is a function from a topological space X to R2, and the same for bold psi. Okay? For each pair AB, where A is a number in the open interval 0, 1, and B is a real number, we can define this map FAB from the space of continuous functions from X to the real plane to the space of continuous functions from X to the real numbers. And this map FAB is defined like this. Okay? The formula could appear weird, maybe, but it is the right one to produce the biparameter, let me say, the reduction from biparameter persistent homology to one parameter persistent homology. What is interesting here for this formula is that FAB is a GENEO. It is in some way comforting to see that this concept that was born for different reason appears in topological data analysis naturally in different places. Now, when we have FAB, for each degree k, we can consider the distance that is defined by this formula. We take the supremum, varying this pair AB in our space, of a matching distance between the persistence diagrams of FAB of bold phi and the persistence diagrams in degree k of FAB of bold psi. This is the distance that is called in literature two-dimensional matching distance. Okay? And it is the distance that is used in several applications to apply by parameter persistent homology. This distance is based on the concept of GENEO. This is the interesting remark. It is worth noting that if we use GENEOs, then we can obtain many different distances for biparametric persistence, different from one that is mostly used in the theory. For example, if we are interested in distances based on one-parameter families of GENEOs, we can define pseudometric in biparametric TDA using this operator, F bar, that is just the convex combination, or ft bar, since you have to choose the parameter t here in the interval, in the closed interval 0, 1. F at t, that is the convex combination of the maximum and the minimum between the functions, or f tilde, that is defined by this formula. Okay? For any choice, we have a different pseudometric. So we haven't just one pseudometric based on two parameters. We can define many different pseudometric, reducing the complexity of managing biparametric persistence. More details about this approach can be found in these papers towards a topological geometrical theory of group equivariant non-expansive operators for data analysis and machine learning. Then a paper by Nicola Quercioli, some new methods to build group equivariant non-expansive operators in TDA. There is this quite recent preprint, the convex matching distance in multi-parameter persistent. And there is also this paper, projected distances for multi-parameter persistence modules, but this concerns a different approach, but is related to this approach. It is not based on GENEOs. It is based on shift theory. Okay, now, I have explained why GENEOs are important and relevant for topological data analysis. Now I would like to spend a few minutes speaking about the application of GENEOs on explainable artificial intelligence. Okay, this is a joint work with Filippo Bonchi, Jacopo Joy Colombini, Francesco Giannini, Fosca Giannotti, and Roberto Pellungrini. More details about what I'm going to say can be found in this paper, Mathematical Foundation of Interpretable Equivariant Surrogate Models, that was presented at the Third World Conference on Explainable Artificial Intelligence. Okay, the basic idea is an idea to answer the following question. How can we mathematically and generally formalize the concept of an explanation provided by an agent viewed as an operator? Maybe you know that when we have a neural network saying something about reality, we need explanation. Since if the neural network says, okay, you need some kind of surgery, maybe it's important that the neural network explains why. Okay, so explanations are quite important in artificial intelligence. The informal idea that we are studying and produced our approach based on GENEOs is the following one. We say that the action of an agent A is explained by another agent B from the perspective of an agent C if C perceives A and B as similar to each other, and C perceives B as less complex than A. Okay? For example, we can consider two neural networks represented by two geos, A and B. Please note that a geo C can take geos A and B as inputs. Okay? Now, to proceed in this way, we need two things. First of all, a pseudometric to compare geos. Okay? a pseudometric between geos that remains well defined even when the geos operate on different domains and produce outputs in distinct codomains. Okay, this is the difficult part. It is pretty simple to define a metric between operators acting on the same data in input and output. What is important is defining a pseudometric between geos defined on different domains and producing outputs in distinct codomains. And then we need a measure of complexity for geos. So if these two vertical arrows represent geos, this is a geo representing the agent A acting on data, transforming data, and this second vertical arrow represents the agent B, we have these questions. We have to answer this question. What's the distance between these two geos? And then we have to answer this question too. What is the complexity of these two agents? Informally speaking, two geos are considered similar in our approach if there exist two horizontal GENEOs represented by these horizontal arrows in this picture that make this diagram nearly commutative, with the same holding true in the opposite direction, okay, when we change the directions of horizontal GENEOs. And the cost function can quantify the non-commutativity of each diagram. Let me explain this in more detail. Let us assume that this black point is a function, okay, or some kind of data, for example, a graph, okay, and we have a geo transforming this graph into, I do not know, a function or a cloud of points. And this new data living in psi, in the space psi alpha, is the green, represented by the green point. But we can also proceed along this red arrow, okay? If we do that, we arrive at another point, the red point, that is in general different from the green point. We can measure the distance, the non-commutativity of this diagram. And this non-commutativity is formally defined by an integral. We need that phi alpha is a Borel space. We can make an integration on phi alpha. We can integrate this distance in order to get a cost function quantifying the non-commutativity of each diagram. Here, I have no time to explain this in detail. But the important statement is that we can use GENEOs in order to define a distance, a cost function in this diagram, and a distance between geos. Anyway, let me give you an example. Suppose we have two neural networks for edge detection in images represented as geos. So we have this neural network that work on high resolution images, and this low neural network, simpler than the previous one, working on low resolution images, okay? Now we can consider any possible GENEOs here. Our choice consists also in considering the space of GENEOs that are legitimate in this game, and we can measure the non-commutativity of this diagram. And we can do the same with while reversing the horizontal arrows, okay? The two neural networks are considered closed with respect to our choice of GENEOs, horizontal GENEOs, if there exist two pairs of horizontal GENEOs that make these diagrams nearly commutative. To formalize our new pseudometric DE between geos, we have to consider the category as whole, whose objects are all perception spaces, and whose morphisms are GENEOs. The morphisms in S whole are called translation GENEOs. These morphisms describe the possible logical correspondences between data represented by different perception spaces. For example, a translation GENEO might transform high-resolution images into low-resolution images, as happens in my example. I omit the technical details of the definition of a distance dE between geos that requires some mathematical structure, and simply observe that the non-expansiveness of translation GENEOs is a key ingredient in its definition. Without that, you do not get a distance, okay? When the distance between two geos is small, it indicates that they act approximately in the same way on the data they process. Maybe You have different machines, different agents. They act on different data, but their action is similar in some sense. Now we need a definition of complexity, and we proceed like this. Let us assume a set gamma of geos is available. We will say that gamma is our internal library. For each geo in this set gamma, we arbitrarily choose a value ci representing the complexity of this operator. The set gamma represents the elementary geos that we can use to build our more complex geos. Let us now consider the closure of gamma, that is the minimal set gamma bar, such that gamma bar includes gamma. Gamma bar is closed under composition and under direct product. Now, each composition and direct product is associated with a complexity. The complexity of each geo is obtained by minimizing the sum of the complexity of the geos that we use and the complexity of the compositions and direct products that we apply to build FT. I have illustrated a model based on composition and direct products, but other form of composition of geos can be added to the model. So we have a theory to build, to put together geos like Lego bricks in order to build more complex network, to do more complex things, okay? And we can insert explainability in this model that is based on GENEOs. Let me conclude this part by saying that we can formalize our mathematical concept of explanation. Specifically, we can define it as follows. After choosing the values epsilon and k, the action of an agent represented by a geo f alpha t alpha is explained at a level epsilon by the action of another agent of complexity less than k, represented by another geo f beta t beta, belonging to our space gamma bar, when the distance is less than epsilon. So the situation is like this. We have real data and real observer. And the scene is pretty complex. We can simplify data and the observer, and this simplification, that is based on our metric and definition of complexity, is an explanation for the previous action. Okay, and now the last example to conclude my talk, reconstruction of sparse urban wireless signals via GENEOs. This is essentially our project with Huawei. We use GENEOs to reconstruct signals. This is just an example of signals, a radio signal in Munich. We just take a very poor sampling of this signal. When I say very poor sampling, I mean 3%, 2% of pixels that are available about the signal. And we add noise to this data. And then we try to reconstruct the data. And this is what happens when we use GENEOs. Okay? This is a joint research with Lorenzo Mario Amorosa, Francesco Conti, Ichong Tagliabellofti Maiari, Nicola Querciori, and Flavio Zabini. And if you need to have more information, you can have a look at this preprint reconstruction of sparse urban wireless signals via group equivariant non-expansive operators. We propose a GENEO-based approach for reconstructing radio signals in urban wireless networks from extremely sparse samples. We describe a signal to be reconstructed as a function phi from the real plane to the closed interval 0, 1. The function phi represents the intensity of a signal over a grid, and is often referred to as ground truth or GT. We also consider the function psi, taking each point of the real plane to the reliability psi of p of a value phi of p measured at that point. We aim at reconstructing phi, the signal, by starting from a very poor sampling of phi, typically 2% or 3% of a ground truth, by using suitable families of GENEOs. And okay, in our experiments, we focus on reconstructing the signal over a two-dimensional area. We generated signal measurements with the Sionna RT ray tracing simulator using its built-in outer urban scenarios for Munich and Paris, and each scenario is discretized. And this is what happens. On the left, you can see here we use 3% of a signal, and the noise is applied to 15% of the pixels. And on the left, you can see the original signal. B represents the result, the reconstruction results given by GENEOs. C represents the reconstruction results given by k-neighbors, method based on k-neighbors. And in D, you can see the results given by a convolutional neural network, UNet. You can see that the quality of B is better. Using GENEOs is advantageous in this application. The same can be seen here. The result given, the construction given by GENEOs is represented in B. And let me skip the diagrams here. I have numbers about this behavior. Here, the lower, the better, and the green is GENEOs, but I skip these details since are not so important from the theoretical point of view. We can quantify the error, and we have a smaller mean square error and smaller one Wasserstein distance between the associated persistence diagrams. But anyway, that's it. This is the takeaway message I'd like to leave to you. To sum up, GENEOs are novel mathematical tools initially developed in TDA and useful for approximating equivariant neural networks using a compositional approach. GENEOs are generally interpretable, making them potentially beneficial for explainable artificial intelligence. That's it. Thank you so much for your attention.
Okay, Patrizio, are there any questions from the audience? I have one, Patrizio, but it's something that we already hinted at in our conversations before. I'm always I always find a limit in the fact that you use rigid groups and rigid subgroups, meaning that within that group all are equal. I mean, of course, I cannot use, if I'm interested in working on written text, I cannot use all affine transformations, okay? But there are some which are more allowed than others, and some which are important. If I have a slanted writing, like italic, I should be able to read it, and so I might need a not so strongly deforming affine transformation, but not all affine transformations are allowed. Does something like the evaluation of the difference element in a transformation group have a place in your theory?
We made some attempts and we wrote some papers about this alternative approach that is based on choosing some structure that is not a group, maybe just a set of transformations that allow for, let me say, weakening the approach. I my opinion about this is that at the very beginning of the development of a theory, we need to have a good theory for groups, and we have to see what happens. For example, I cited the representation theorem, okay, as an example. What happens when we consider groups? But it is possible to weaken the theory and to add errors in the transformation we are considering. So the line of research we are speaking about is quite interesting, and we are considering this possibility of changing the formalism and the mathematical structure. But I guess that at this stage, we have first to develop let me say, a strong theory for the general case. At least this is my view of the problem.
One step after the other. Lucy Kernitz.
Yeah, thank you. So I have two questions. Actually, the first one is kind of similar to the previous question, and I just wanted to confirm, you talked about task bias at the start. So do you think about that as kind of like every task has a restriction in the space of GENEOs given the data set?
Which kind of restriction are you considering restriction
So for
about
example,
data,
like
about the action of the group, or about the
yeah, yeah, action of the group, because depending on what task I have, like some actions maybe, for example, if I have like pictures of like dogs and cats and like what I want to learn is classification, rotational symmetry may be fine. But if I want to learn how to generate pictures of dogs, that people would find acceptable, then I don't want to see an upside down dog. So, yeah.
Yeah, as I was telling previously, we have some paper about this, where we do not require that. Essentially, we consider this approach. You know that there are several approaches to consider the problem you described, and our approach was this one in this paper. We consider signals that are taken to another larger space, and there is a chain of larger and larger spaces where you can move your signals. When you apply your GENEO, it is not legitimate to apply once again your GENEO if the data does not belong to the initial space.
Mhm.
So you cannot iterate your transformation. There are some limitations in the way you treat your data. But I guess that these problems, this is my personal feeling, can be managed without too many difficulties from the mathematical point of view. What I think is that the most important part of a theory is measuring how much we can reduce the complexity of the problem when since maybe I did not stress this point. In the application concerning pockets in proteins, for example, we have comparison with the state of the art techniques to find pockets. And one of the competitor in this problem is a convolutional neural network that is used to find pockets in proteins. It is a small neural network with around 500,000 parameters. Okay, but we obtained better results using a GENEO based on 17 parameters. Since GENEOs reduce the complexity of the problem in a huge way, and they do that because they can split the problem in some sense in many independent problems, so that the final complexity is pretty low. So I completely agree with your implicit question about the way we can adapt the theory in order to solve the problems you stressed. I guess that I'm confident that it is not a big difficulty from the mathematical point of view, but I think that the real difficulty is in finding a good mathematical theory for example, what I said about representing GENEOs, that is building GENEOs, having a technique to build GENEOs. When we have a problem, okay, we have to build GENEOs in order to compose them into a network, okay? So the problem is, how can you build GENEOs suitable for that problem? So we need theorems. And the representation theorem says, okay, if you are able to build permutant measures, you are able to build GENEOs. Okay? But that theorem just works for linear GENEOs. not for any GENEOs. So we need a lot of new mathematics in order to manage the theory that we are developing. And this is very, in my opinion, this is a very real problem.
Okay, thank you. The other question I had maybe actually touches on some of what you mentioned, but I was interested if some of this can be used to study generalization. And I guess the way I understand it, your perception space is defined as on like the finite data space. But I would be interested in whether some of this can be, I guess, like extended to the view that we are really estimating some underlying distribution up to, like a specific task. Do you think that's like a
Uh,
viable?
okay, uh, we have a preprint about probability distribution on the space of data, and an adaptation of the concept of GENEO and the corresponding concept about, for example, non-expansiveness that are built on this probability distribution on data.
Okay,
Since
great.
it's quite natural to say not any data is equally likely, probable in an experiment. So we have to take this into account. There are so many different lines of research, and I'm not a probabilist. So if you are able to work on this, it will be great.
Okay, great. Thank you.
Teresa, don't forget to write the site where to find your slides
Okay,
before
maybe
stop the recording.
uh, yes, maybe I can write this in the chat.
Yeah, yeah.
It's, just one moment, since I should copy this, and then uh, okay, okay. So if you are interested, you can find my slides at
Okay.
this link.
I must say that I was amazed by the idea of formalizing the explanation. This is great. I appreciate it very much. Are there any other questions? But we are a bit over time. No other questions. So thank you, Patrizio. And okay.
Thank you so much. Thank you so much.